you guys can't tell, the secret is we are side by side running the AV for this conference. So we're really excited to be in front of everybody, and we really enjoy interacting with customers and being at conferences and hearing what you guys are up to, getting feedback, and we miss it. This is a good replacement, but it's not the same. So we are excited to be part of something we think is big, but we hope to be like in front of you in your classrooms here again soon. So I want to thank all the amazing teachers that are probably juggling, barking dogs and crying children and working on their classrooms remotely, that are here with us, the administrators that are, I think, supporting your teachers, maybe the pre-service teachers that are still in school and trying to figure out, like, how do you continue learning and getting trained in this remote distance learning environment. So we're all in the same boat with you, and we're glad that we have this community that is still passionate about science, and that is, we're continuing to go about our education and our business and what we can, while being mindful of the shutdown that's in place. So I'm excited to be here with you guys, and let me start with the basics. So what you are seeing here for my presentation is using PocketLab Notebook. And so what we like to say is we want to eat our own dog food, and we're going to present to you using our own platform. And this is nice because at the end of this, we'll send links to our presentation and our resources that you can then modify or use as is for yourself to learn the platform, or you can push to your students so that they can do something hands-on in this remote learning environment. So let's start with the very basics of what is PocketLab Notebook, and that's what we'll be focusing on today. And it's a digital lab notebook that we use for online science labs. And typically these science labs are hands-on, but in this remote learning environment, some of them will be just the data analysis from data that we collected hands-on, or that you as a teacher could collect and then push to your students if they don't have any way to get that data. So if you are at a computer, or after this, after you are done paying attention to all the presentations today, go to thepocketlab.com/app, and you can create a free account to start using the PocketLab Notebook. And I'm going to talk to you in two parts today. The first one is an overview of PocketLab and what our mission is. And then the second part is going through an activity. This is a pretty simple activity that doesn't need a whole lot of background information on the albedo effect. And we have devised two ways for you to do this activity. One is with pre-recorded experimental data that's within PocketLab Notebook that you could have students analyze, or you could analyze and do a demonstration with your students. And then there's also a way for you to push this activity using household supplies like a kitchen thermometer, meat thermometer. And it's not as rich a data set as if you had a lab full of equipment, but it doesn't require a whole lot. So that's where we'll start. So my co-founder, Dave, gave me a great introduction, and my background is in sensors, and my life has been about sensors, and it's a great passion of mine to be able to use so the latest generation, the latest innovations in sensor technology in something like science education. So our mission is that we want students to do authentic data collection, authentic science in a fun, engaging, and accessible way. Recipe kinds of activities and science experiments are useful in certain contexts, but if we can get students asking questions that are interesting to them and then equip them with tools to go out and investigate that, that's really when you get the greatest amount of learning, and that's what we're driving towards. So the mission of PocketLab is to do these sorts of authentic questions at a level that is appropriate for the student. So if that's a second grade student, it's going to be a lot different question that they're asking than an AP physics student. And the thing I want to emphasize is that PocketLab, the products that we make, they're simple, but they're powerful. We use them with third graders to ask questions like, what is in the air that we breathe? And then we use it with graduate mechanical engineering students, looking at things like the moments of inertia of complex geometries, damped harmonic motion, three-dimensional kinematics. So it's simple and you can get started at a very young age, but we have researchers that use it for real-world data collection. So we want to emphasize both sides. In terms of support, this is always an early question that we get. PocketLab works with any device, computer, tablet, smartphone, Chromebook, and we make it simple so that on any computer or Chromebook, you don't even have to download an app. It'll just run in your browser. So it simplifies a lot of the IT. And then on Android or iOS, there are apps that you can download from the App Store, and those are free. So you don't need any sort of code. It makes getting started as easy as possible. We make notebook software, which I'm going through right now. And then we also make hardware devices, sensors. And this one here on the slide and in my hand is called PocketLab Voyager. And this is designed for physics and physical science. It can measure motion, altitude, light, and magnetic fields. And we think of it as like a Swiss Army knife for your physics lab. So I have within my presentation some live data coming from this PocketLab. It's sending it to my computer using Bluetooth. And I don't know if there's going to be latency on your side of things as the data is coming through, but it's in real time, normally if you're not running a video conferencing app. So I'm going to put it in a giant Ziploc bag here. I'm going to seal this bag. And what I'm showing is a line graph of the pressure inside this bag. So you can measure barometric pressure, which pertains to how the weather is like outside, or if you're applying some added air pressure, we change the barometric pressure reading here. And so I'm just sort of gently squeezing this bag, and hopefully you can see the data change in real time. So that's PocketLab Voyager. We use it with third graders to look at the basics of motion and forces, and we use it with graduate students to look at three-dimensional mechanics. The other main product we have right now is called PocketLab Air. And this is our environmental sensor. And we have designed it to be the Swiss Army knife for studying the climate and air quality. So it can measure CO2, ozone, small particles in the air, so particulate matter that's less than 10 microns in size, and then the ambient weather conditions like temperature, barometric pressure, humidity, and light intensity. So below here, I have real-time data coming from my PocketLab Air, right here. So it's measuring the small particles here in the dining room where we're at, and you can see that the air is pretty clean. We don't have a whole lot of particles. The ozone is low, which we expect. The CO2 is kind of high because it's been hanging out like underneath me as I talk. And so as I exhale, it's picking up the CO2. And if I go blow on it, you'll start to see that graph change in real time. And then we also calculate an air quality score, show the local weather conditions, and then we can pull in data from local EPA or air quality management district sites. So this map shows nearby what our AQI is, our air quality index in stations. So today it's very good, as you would expect, because hopefully nobody's on the road. Nobody's driving around and creating emissions. So within this lab notebook tool that I'm taking you through, it's a good way to do presentations like this, but it's really designed for a student to do a lab report. And lab reports are probably the worst part of science, in my opinion. Like, it's fun to do these science experiments, but then you have to write everything up and analyze your data and be rigorous about it. There's a lot, it can be tedious, and it can be very difficult for a 6th grade student to tackle. But we've tried to make that easy, putting in the necessary tools for a student to create a lab report and for a teacher to administer that in their classroom. So, like many of the other companies, we are offering free access to our software to help in this remote learning time. So any attendee from the Science is Cool Unconference can sign up for an account, and you will automatically get a free trial. And then we are extending all free trials through the summer so that anybody wants to do any of these activities with their students, they can get started without having to pay any money. So we will be sharing these resources along with everybody else's resources in a follow-up email after the conference. But here are some links that you can see, and they're fairly straightforward to type in if you wanted to get started right away. Go to the PocketLab.com/app, and you can create an account as soon as you want. Okay, so that's PocketLab as an overview, and let me get specifically into the albedo effect. Okay, so we are now in a sort of a similar panel of PocketLab Notebook. This is a lab report, and this is something that you can see as an educator and preview as an activity. You can then download into your account, and you can use it as is, or you can delete anything that you want. You can move the text and the images around. You can add your own data. And then whenever you're done with it, you can then take it and assign it to all your students. So we'll be going through the albedo effect in this way. We wrote this lesson targeted at middle school physical science. So if you have upper elementary school students, you could probably scaffold it down. If you have freshman high schoolers, then you could probably scaffold it up. So the albedo effect, even if you don't know it by name, you're probably very familiar with it. It's the reason why on a hot sunny day, if you're wearing a white t-shirt or a black t-shirt, you'll be experiencing different temperature. It's also one of the reasons why, blacktop in a parking lot is hotter than more reflective surfaces. And the goal of this activity is for students to understand how the color of an object affects the temperature of that object in sunlight. And there are 2 ways to do that, or 3 ways to do that. If you were in your classroom and you had PocketLab sensors, you could do it with them. Now in this remote learning, if you happen to have students with PocketLabs out there, you could do it in the same way. But we've recorded data for you just to be able to do the data analysis portion, or you can do a similar experiment that is, we've taken out some of the complexity using an at-home like meat thermometer or alcohol thermometer. So the scientific phenomenon that we're investigating is that we know light can be absorbed and reflected from an object. And it's logical for us to then say that we know that different colors absorb and reflect light differently. That's obvious because that's why we see colors. So this can affect the amount of heat, sort of radiation that's being absorbed from sources like a heat lamp or the sunlight more commonly. And that can cause things to get hotter than other objects. A local news station did a great illustration with using crayons, and embedded into our lab report is a YouTube video that you can have students watch and then answer questions about afterwards. I won't play it for you, but that is viewable within the lab report. And what they did on a very hot, sunny day was tape crayons onto a piece of foam board, and you can see that the black crayons and the dark colored crayons start to melt before the light colored crayons. So this being early April, probably in many places where you guys are, you can't do this activity yet. I think crayons typically start to soften around 120 degrees Fahrenheit. But this would be a good way to do it during the summer. So if you sent this to your students, then you could ask them to give pre-lab observations. And so this question is embedded into the lab report, and students could submit their responses to this, which pop up in the teacher dashboard, which I'm not going to show today, but know that you can explore this when you sign up for a free account. We then structure these activities for students to form a hypothesis around the investigating question for them to ask, like, how does the color of an object affect the temperature of the object in sunlight? And for this experiment, since it's at a middle school level, we give a pretty rigorous lab procedure. And I would say one modification, if you're using this with high schoolers, is that you could have them design their own procedure so that there's more, there's another component of the NGSS that they're doing, another science and engineering practice. But for middle school students, this might be a good starting point, especially if they're getting used to the platform as a whole. Like, what is Notebook and how does this all work together? So the materials for this lab are a thermometer and some construction paper of different colors. And if you have a heat lamp, you could do this inside. But if it's sunny, it's great to do this outside, where you create a jacket out of the different colored construction paper for your thermometer. You put it in there, and then you record observations over time. And there's a table in here where students then can put in their data based on the time points: 1 minute, 2 minutes, 3 minutes, 4 minutes. And then there are data analysis questions to go into detail about and guide them through what's going on. Okay, so that's how you can use it at home and doing what's a real hands-on science experiment. If you want students to do the data analysis portion, we have collected data for you already. And so here's our setup that I did in my house using a heat lamp and 2 colored pieces of paper, black and white, and then using our temperature probe that plugs into our Voyager sensor. And then here's our data from this experiment. So here's a line graph of the temperature over time. The axis on the bottom is seconds. So we go up to about 900 seconds. So, like 15 minutes. And then the temperature change. And you can see at time 0 to about a minute, I had the lamp off, and it's a stable low temperature, about 20 degrees C. And then I turned the lamp on. And that red line is the temperature probe that's within the black jacket. And that blue line is the temperature probe within the white jacket. And you can see over time how the temperature diverges. And after 10, 12 minutes, the black jacket is reading about 34.5 degrees C, and the white one is 32.4 degrees C. And you can see that sort of that asymptotic rise of the temperature. We didn't quite get to 0 on the slope, so the temperature was still changing and going up slowly, but I was getting a little bored after 20 minutes, so I shut down the data collection. And within Notebook, you can hover over data points to get that exact data point, and then you can pinch and zoom so that you can focus in on a portion of the graph. So you can see here at the beginning that our temperature was very close together at about 70 seconds, and then it starts to diverge as they heat up. the albedo effect in action. And so using black and white pieces of paper is, I think, the most straightforward implementation of this. And the hypothesis is, I think, fairly straightforward to guess. Here's a little bit more difficult one that before doing it, I didn't know what the right answer would be. And here is an array of 4 pieces of paper, red, blue, green, and yellow in the same setup, now with 4 temperature probes, and looking comparatively at the temperature change there. So we don't have a poll for this one, but ask yourself, which do you think is the paper that'll heat up the most? And our evidence suggests that the blue paper absorbs the most heat from our heat lamp. The yellow and red paper were very close. You can't really distinguish which one has changed more. And then the green one is by far, has by far the smallest temperature rise. And this one took a while to settle out. You can see that this on the bottom graph, it's in seconds again, and this runs for almost 30 minutes so that we can really see it settle out. And then it takes a while. So if we were to zoom in on some of the earlier parts of the graph, it's not obvious which color is heating up faster. So if you just did this experiment over 2 minutes, I think your data would be pretty inconclusive. It takes about 30 minutes for you to really get sort of spread in your experimental setup. And then I think it's a good question if we rearranged the colors to be in different spots underneath the heat lamp, would this change? That would be a second trial that we could do. What is the spectrum of light that's coming out of this heat lamp? Is it like sunlight, or how different is it? And would this experiment be different if we did it in direct sunlight? So these are extension questions that if you're working with a high school group of students, you could really push them to think about these things. And then like one of our presenters before, ADI, they use sort of a claim, evidence, reason way to tie up a lab. That's what we generally emphasize in the way we write our materials. So after doing the experiment, we want students to come up with their claim, their evidence, and their reasoning. And all of this students can put into the lab report and type their responses, add videos, add images, and make this very powerful multimedia document. And then we have some suggestions for lab extensions, using crayons or doing using other materials. You could use sand and charcoal. You could look at ice, it's a simple concept, like different materials absorb and reflect different amounts of energy, but there's a lot that you can then go out and explore further. So that's why we really like it. Start simple and then has a lot of potential. Okay, so I'm going to show you where these exist. So if you log into the PocketLab notebook, and after you go through the login screen, here are our resources that we have, starting points for you that we have developed. And there are about 15 of them in here right now. We just launched Notebook about 3 months ago. So we're building out our content, and pretty soon we'll have sort of full sequence of content for middle school physical science and then high school physics, as well as sort of specific activities for environmental science around PocketLab Air. But you can see some of the things that we're doing around looking at analog and digital signals, motion, the color and temperature of objects is here. And this is the lab report that I just took you through. The other resource that is very timely and that you can easily do without needing any kind of equipment is this lab report around data from the 1918 influenza pandemic and how social distancing helped one city and really hurt another city in their response to the virus. So I will just give a preview of this. Here is data from two cities, Philadelphia and St. Louis. Philadelphia is in red and St. Louis is in blue. And this is on the x-axis is days after September 14th, when the pandemic started to hit the US. And the data in red has a very big spike. This is in Philadelphia. There was a big parade that day, or a few days earlier in Philadelphia, that led to this spike. In contrast, St. Louis canceled their parade and took early steps to do social distancing. And you can see that they really flattened the curve. And here's data that students can click on, pinch and zoom and hover over individual data points so they can interact with it. And then a few sort of straightforward explanations and questions to get students thinking about analyzing this data. So all of this is within PocketLab Notebook, freely available to any educators that sign up and get started. And we are trying to support all of our users, all of our existing users using this. And then everybody new that is wanting to take maybe one activity, one lesson, and test it out for themselves, or see if they can push it to their students and what they're able to do as we're all learning about sort of remote learning and distance learning and how to best tackle that. So we are here for your support, and we will send out links like everybody else will to these resources in follow-up emails after the conference. So thank you so much for your attention. I know, like, I have a 2-year-old at home, and it can be difficult to give attention to these things and juggle everything that's going on with this remote working. And we thank you for this opportunity to talk with you. And hopefully we'll do some questions, and we will try to avoid any feedback as Dave and I are sitting right next to each other.
Great, thanks, Cliff. Yeah, this is fantastic. Thank you very much. A lot of nice comments. Hey, a couple questions. So what do people need to run this? What kind of browser, computer, or anything do they need?
Good question. It runs on any device, so Mac, Chromebook, Windows computer, even an Android tablet or phone. If you need to connect to sensors, we use Bluetooth through your internet browser. The only browser that fully supports Bluetooth right now is Chrome. So if you want to connect to a PocketLab sensor and see data live, you need to use your Chrome browser. You can access some portions of the notebook through any other browser, Safari, Edge, Firefox, but it works best in Chrome.
Okay, and then so somebody who wants to use this can use this now. Basically, they can go use it. It's free. It's available.
Yeah. Yes, and even if you want to do, there is one sensor built into your everybody's computer or Chromebook, and that's your microphone. So we do have a way for you to measure sound levels if you're using Notebook without devices. But it's way more fun to be able to measure the CO2 concentration in the air, or measure the the air pressure inside a Ziploc bag, which we can't fit your Chromebook into a Ziploc bag, nor does it have CO2 sensors built in. So sensors are pretty powerful, and they unlock a lot of things in science that you can otherwise do.
Great. Hey, interesting question came in here. What to do for elementary students?
That's a good question, and we have some other resources available on our educators page that are not yet in Notebook. So if you go to PocketLab.com and click on educators, there are 20 elementary school activities there. So some basic ones are around weather, understanding what something like surface temperature is. So going out and measuring the black top and how hot that is, and then going out and measuring temperature underneath a shady tree. And so that would be a way to get at this albedo effect. Also, the basics of motion in terms of force and collisions. If you're an NGSS state, those come up a lot in 3rd and 4th grade. And we have some scaffolded activities that are like 4th graders love them. They do really well. And it can be scary to start out at first, but students get the hang of it way faster than I would even ever expect.
You know, somebody asked a follow, I think the same person asked a follow-up question. It's a good question. It might be useful to use this when there are forest fires. I have no idea where they are. They, you know, could be here, it could be a lot of places that are experiencing that now.
Yeah, unfortunately, when the wildfires were raging a year and a half ago in California, the data was very interesting, and you could,
yeah.
Sorry, yeah. And we had devices set up all around our office, in our homes. I would look at sort of the air quality maps that were available from the EPA, and then go out and take personal measurements. We used it while we were out running, outside to, you could find some cold spots, like where you might be in a valley or there's good tree coverage. So it was interesting data, but yeah, very useful in creating science experiments when something like that is going on.
You know, just a funny story. We were at the office, and there was a fire nearby from the highway. There was actually on the walls that they put up for the sound isolation, there was ivy growing on there that had dried out. So Robbie and I walked down a couple blocks to see that. We brought our PocketLab air, and the smoke was really intense, and it traveled really far, and you could actually measure it, and you could see it increasing, as you got closer. So it was really useful. There's another question here. Let me see. Air quality. Oh yeah. Would you? So this is a tricky but a good question. Kind of interesting question. Would you use this kind of evidence to shut down the school or to take measures?
I don't know if I would, how actionable it is. It is high quality, and the measurements are very valid, but you do have to be careful the sort of the conclusions that you draw from air quality data. Air quality specifically, when you look at data from the EPA, it's average over an hour time frame, or 24 hours. And that's what we have health data around. So if you collect like a point measurement that's over sort of 5 minutes, and you want to take action on that, you got to understand what the data means and put it in context. But it is very high quality data. We've spent a lot of time on testing it, but we've never used it for those sorts of monitoring applications.
So you'd have to be careful thinking about what does this data mean for the environment I'm in, and how to interpret it.
Right.
Another question here that popped up is, do PocketLab ship internationally?
Yeah, everything comes through our office, and we see every label that goes out. And we do have some international resellers in certain geographies in Australia and Japan. Or if we don't have a local reseller, then yes, it'll come from our global headquarters here in San Jose to your doorstep.
So actually made in California.
Yes.
That's good to know. Another interesting question popped up while we're talking. So is there any future PocketLab to use in an aquatic environment?
Yes, we've been getting this question a lot, and it is something that we are actively working on. The 3 things that have come up are, you want to measure the temperature of the water, the solution, pH, and then so those are the 2 most obvious ones. Then salinity and turbidity, and dissolved oxygen if possible. So yeah, we're working on it and figuring out a way to keep with our mission of making things simple, bring down the cost of these probes. Something like measuring dissolved oxygen is an expensive measurement. So one of our jobs is to figure out how we can reduce that cost to make it more affordable for all our teachers.
Great, great. Good to know. And what another interesting question came up is, I think it's another tricky one. Have insurance companies asked you to provide PocketLab Air data for asthmatics for self-assessment and treatment? And the person noted that they're registered nurse.
Oh, we have had research projects and student projects that are looking at those questions. We have not had insurance companies come to us. We've had political action committees that have come to us to look at air quality and emissions in the city. So people have lots of ideas, and we want to enable them. We don't get super involved with many of the projects, though.
Interesting. You know, just a quick question. There's a "where can I buy it now" question. You may tell them where the website is and how to do that.
Yeah, if you Google PocketLab, you'll get the first. We're all the hits, which is good. But thepocketlab.com, just type that into your URL bar, and then if you go to thepocketlab.com/app, you can create your free notebook account and get started with that.
Great, great. And last important question: do you agree with Eugene about Levitt being the best burrito?
I haven't eaten there, so he's got to take me out.
Okay, well, okay. Let's just send a message and get that in there.
Yeah.
Okay, great. Well, that's fantastic. Cliff, thank you very much.